So we're doing parametric functions. Homework Wednesday will be finalized by 5 p.m. tonight. So there may be more written. There's going to be web work. So after 5, you'll know that that's everything you need to do tonight, 5 p.m. on Blackboard. Okay, just a quick recap of the basics. Parametric functions have this form. X is a function of t and y is another function of t. So our independent variable is now t. It used to be what? What did the independent variable used to be? X. And the dependent variable was? Or that's what we use the most often, right? But we've talked about all kinds of quantities in this course, right? And but in terms of graphing in the xy plane, we usually on the horizontal axis we usually put the independent, and then the vertical axis the dependent. But now this is kind of a different beast here. So the independent variable is t, and what axis does that go on? Doesn't, right? So it's like a behind the scenes. The independent variable is, it's varying. You know, variables vary. It's varying behind the scenes and generating what? What's the dependent thing? What's the dependent variable? Yeah, so now the dependent variable, quote, variable is now an ordered pair, right? So it's like the dependent thing. So as t varies, we get correspondence points that vary, right? So x and y vary, and then we graph that. We graph that in the xy plane, so then t is kind of behind the scenes, right? It doesn't have an axis that we're showing the variation of t on. We just see the correspondence points varying in the xy plane, but that was determined by t, right? So, which is kind of invisible. All right. So that's just kind of the ground rules, right? Ground rules. So let's just put that on hold for a second and do a review. So let's pretend this is the final exam. There's one question on the final exam. One question. Here it is. Will you pass the final exam? What's the meaning of dy dx, the rate of change of y with respect to x? Pretend it's the final. This is the one question. So we worked hard on this for at least a month at the beginning of the course. And those of you who had Calc 1 with us, the whole course. Okay? So, and if you want to suppose it's 2.5 to help you form a response, that's fine. So you can suppose it's a number, this number 2.5, but it could be anything. What's the meaning of dy dx? She said for every change in x, y changes by dy dx times that change in x, or in this case 2.5. So for any change in x, y would change by 2.5 times the change in x. 90%. A on the final. She got a 90. She got an A in the final. But it's not 100%. Why not? Alex. Okay, so it's got to be a small change, right? If you have a varying rate of change, it would need to be a very small change in x. And then you could make that assumption that y changes by 2.5 times as much as the change in x. If it's so she answered what question? A slightly different question. If dy dx was a constant rate of change, right? If it was a constant rate of change, then her answer was perfect, because for any change in x, the change in y would be 2.5 times the change in x. Okay? But if you don't know, if the rate might be changing, right? The rate might be changing, then this only works for really small values of x, right? Like on a curve, you got to zoom in far enough to see it being linear, right? And then this works. Okay, how did you do? Just self-assessment. So this is kind of like one of the hugest things that in the last 2 semesters, we've been trying to get across, that dy dx, the phrase rate of change has meaning, right? It means it's this number that tells us how x and y are changing together. Given any little change in x, y changes how much compared to x, right? So that's what we mean by rate of change. Okay, so then, what would dx dt mean? And so now bringing this principle back to parametric functions, what would dx dt mean and what would dy dt mean? Tell the person next to you. What would dx dt mean and what would dy dt mean? Tell the person next to you. Go. Justin, tell me. What does dx dt mean? What's that? Oh, break my heart. No. How about Tristan? What does dx dt mean? For a small change in t? Right. So for a small, he says for a small change in t, x will change how much? This much times as much as your dt, right? So for any small change in t, your change in x would be this times as much as the change in t. All right, and what about dy dt? Jennifer, in the back there. What's dy dt mean? Perfect. Yeah, good. Yeah. So given a small change in t, y will change by this much times that change in t. Right? Are we getting the hang of it? All right. So we'll keep that in mind. So let's go back and look. Let's just briefly talk about the where we left off last time. So last time we said that we had to figure out what the parameter was, right? And we figured that the most convenient parameter for graphing these two quantities separately. So the quantities we want related together are Jacob's distance from Casa Grande and Jacob's distance from Maricopa as he travels down the highway. And so we said this is going to be a lot more manageable if we have a parameter or this a behind-the-scenes variable from which we can get those two quantities separately. And then from those two graphs, we could put together the graph that we want, distance from Casa Grande in relation to distance from Maricopa. So what was the parameter we said? The behind-the-scenes variable that made this possible. What did we say? Yeah, distance traveled down the road. Jacob's distance traveled down the road. And those individual graphs should be not so bad, right? So you're just going to think about so we marked off like equal distances right here, so we could kind of get some idea. So mark off equal distances down the road, and then do each of these, find the corresponding distance to Casa Grande. So what's at the beginning? Distance from Casa Grande is doing what as Jacob travels down the road? Increasing? Decreasing until he's about here, and then increasing. All right, and then the distance at the end compares how to the distance at the beginning? Much further, right? So he's kind of close at first and getting closer, and then starts getting further away and gets much further away than he was at the beginning. So what would that graph look like? And then similarly, distance from Maricopa starting was greater. And then what happens as he's moving down the highway? That distance to Maricopa is decreasing until maybe a minimum of here. And then after that, increasing again. Okay? And so that's how you're going to think about putting together those individual graphs. And then from the individual graphs, we can kind of try to construct the distance from Casa Grande. And remember, this was a typo on the sheet. Actually, this was supposed to be Maricopa here. Okay, it's the best sideways drawing I've done all day, writing. Okay. All right, Maricopa. So distance from Maricopa, not Casa Grande. There. And then you're going to look at so you're going to gather. For the same distance traveled, you can get a correspondence point of these two quantities, and then do another distance traveled, get another correspondence point. And so that you're going to finish this for Wednesday, you're going to come up with what this relationship is. Okay, questions on that task? We're going to finish that for Wednesday. Yes, sir. I'll post this. I'll just post it online. All right, other questions? Okay, so I got another one here. Does it still? Oh, yes. So here I'm going to show you a parametric function being generated. And I'm showing you what t is as this function is generated. And what we want to come up with is now the individual. So it's kind of working backwards now. I'm showing you the finished product. I'm showing you the finished product of x is some function of t and y is some other function of t, and these are all those correspondence points for different t's, right? In fact, this is all the t's from 0 to 4. So what we want to do is kind of try to deduce what could the original x and y functions be. So here's what you're going to do to do that. We want to, from what you're seeing here in the graph, we want to kind of gather information. We've got t, and we've got x, and we've got y. And so we're not gonna get individual points, but we're gonna look at like ranges, how all these things are varying together, So what's the first range that makes sense to look at here? So look at it. Watch. Ready? Here we go. T is now 0, and there's 1, and now t is 2, and now t is 3, and then 4. So let's think about what's the first range that would make sense to analyze here. 0 to 1, right? 0 to 1 is this kind of first quarter of it, right? So as t goes from 0 to 1, you're going to write down what does the x coordinates of the points do. So you just got to focus on as t is varying from 0 to 1, what is the x doing? What is x is varying from what to what, or what to what to what, okay? And then same thing with y. So just focusing as t goes from 0 to 1, how does y vary? And then what's the next range of t you should look at? 1 to 2. So the way this is set up, that's kind of obvious, like that. So as I'm taking attendance, you are looking at as t varies from 0 to 1, just the x coordinates of the correspondence points, just the x coordinates of points generally do what, right? Generally do what? So, and then similarly, just the y coordinates of those points. And so by getting these ranges, or how x and y change in these different intervals of t, well, maybe then you can brainstorm on some ideas of what these x and y functions might be like, right? So because x is some function of t, and y is some function of t, and that's what we're trying to figure out. All right, is the task clear? Let's just do x. As t goes from 0 to 1, just focusing on the x coordinate, what does x do? It starts at what? 0. Goes to? Is that it? Okay, yeah, you're getting it. That's right. That's what x does. As t goes from 0 to 1, throughout that range of t, x makes it out to 1 and back to 0 in that range of t. 0 to 1, okay? So or maybe it was so easy that you're done with the whole table. Is that what it was? Pretty easy. Okay, great. I'll take more attendance later. All right, so what? Now we got to figure out what x and y are based on what's happening here. So what happens as x goes from 1 to 2? 0 to negative 1 to 0, and then? So what function, now you got to think of this is not the independent, this is like for the whatever function we have for x, this is the dependent variable, right? It's what's coming out, or like what you would think of as normally on the y-axis, right? Because x is now some function of t, meaning if we were to graph that, we'd put x vertically, right? So what function does this? What function has y values or a dependent variable that goes 0, 1, 0, negative 1, 0, 1, 0, negative 1? Okay? And then similarly with y, what'd you get for y? Y goes from 1 to 0, 0 to 1, 0 to negative 1, right? And then negative 1 to 0, and then back to 1. What about that? Okay, so I think most of you said x is going to have something to do with sine. Sine of something, right? And y has something to do with cosine, right? Because it has that same pattern, but it starts when your independent is 1. Sorry, when independent is 0, cosine is 1. So cosine of something. So that's your next task. We got to make it work, right? So we got to make it work. So as t goes from 0 to 1, the sine function goes from 0 to 1 to 0. So how are we going to get an expression of t in there? This is called the argument. The argument of sine is going to be an expression of t that's going to produce this. And then this, etc. So it's got to work as t varies from 0 to 1, 1 to 2, 2 to 3. The sine is going to trace through just how we have it mapped out. Same with cosine. So it's going to be different for cosine, right? Because it's kind of going through cosine at a different rate, right? So what argument of cosine are you going to need to make it work? So I'll give you a minute or two. I'll keep doing attendance. Figure that out. What x is the argument's going to be some expression of t to make it work, just like the table. So what do you think the x function is? Sine of what? What's that? Sine of pi? Pi t. You want sine of pi t. So here's the beauty of it. If you have a inkling, you can write it down, and then what can you do? Just test it, right? Just see if it's right. So as t goes from 0 to 1, what will pi t do? Pi t will go from what to what? So as t goes from 0 to 1, pi t will go from 0 to pi. And as the argument goes from 0 to pi, does sine go from 0 to 1 to 0? That's exactly what it does, right? It goes, so when you go from 0 to pi in sine, you go from 0 to 1 to 0. And then try the next one. As t goes from 1 to 2, what does pi t do? Goes from? Nope. As t goes from 1 to 2, pi t goes from pi to 2 pi. Right? When t is 1, you get pi. When t is 2. So when you go from pi to 2 pi, what does sine do? 0 to negative 1 back to 0. Is that what we have? That's what we got. Looks right. All right. What about the y variable? Mark, what do you think? Pi t again? You must pi t again. Does it work? Agree with that? Dylan? So as t goes from 0 to 1, we need y to go from 1 to 0. Right? So then we're talking about cosine now. So we need to go from 1 to 0. And so where does it hit 0? Pi over 2, right? So as t goes from 0 to 1, we need the y coordinate of cosine to go from 1 to 0, and that happens at pi over 2. So what'd you get? He wants pi over 2 times t. Does it check out? Does this work now? Okay, do you see what we're doing? Any questions on that? So sine pi t and cosine pi over 2t is how we get this. And you can check go ahead and check it for all 4 ranges, 1 to 2, 2 to 3, and 3 to 4. and you check it against sine pi t and cosine pi over 2t, and you'll see that everything checks out. Any questions on doing that? Anybody? Question? All right, so now the resulting graph is the graph of the parametric function in the xy plane. And I said parametric function. Is it a function? I see people shaking their heads. Is it a function? Why not? Oh, okay, so that doesn't pass the vertical line test. What is that? What's the vertical line test about? What's the vertical line test about? For every x, there is one corresponding y. Or for every value of the independent, there is one corresponding value of dependent. So is that a true statement? For every value of the independent, there's one corresponding value of the dependent. True statement or not? Is it a true statement or not for this graph? What's that?
I'd say it's true.
Why?
There's for every value of the independent variable, which is
t,
there's only one corresponding dependent variable, which is the ordered pair of x, y.
You already said? So is that true? For if you pick a value of t, do you only get one and only ordered pair x, y? Is that true? For every t, you get one ordered pair x, y. Is it true? If it's not, give me an example of where you put in a t and you get two different ordered pairs. Give me an example of a t value that you put in and you get two different ordered pairs. Does that ever happen? Because I'm going to put in a t, I'm going to get one and only one x, right? And if I put in a t, I'm going to get one and only one y. So that means there's only one ordered pair for every t that you pick. What were we going to say, Caden? Okay. So we've got, at two different t values, we get the same x, y. That's what that's saying. Does that violate what a function is? Does it violate what a function is? It doesn't, right? So at two different t's, we can get the same x, y, just like in functions just like in functions from before, even like sine or cosine. There's multiple values of the independent that give you the same dependent, but that's not what the function, that's not the criteria, right? The criteria is, given every individual t, you only get out one value of the dependent. Okay, so is this a function or not? Yes. No. If I just ask you, is it a function? What's that? Because?
Well, if it's a function with respect to t, but it's not a function of x and y.
Right. So the question you initially answered was, is y a function of x? Is y a function of x? No, right? Given x values, there's more than one y, right? And that's the idea of the vertical line test. So given an x, there's more than one y. So if I ask you if y is a function of x, the answer is no. Okay? But are ordered pairs a function of t? Yes. Given any t, you only get one ordered pair from this set of parametric equations. So if I say, is it a function or not? Well, it depends. What are you talking about? Are you talking y is a function of x? Then that was your initial instinct was no, right? But if you're talking about a parametric function, this is absolutely a parametric function because given any t, you only get one ordered pair corresponding to that t. Okay? So with parametric functions, we can graph and talk about a whole new whole new world of functions that we couldn't before. Functions where y is not a function of x, but it's still a function, right? So y is not a function of x, but things like this that cross over themselves and head back and forth, and so we get functions that we're not used to seeing conventionally, but they're still functions because for any t, there's only one corresponding ordered pair for that t. Is the point made? Does that make sense? Okay, here's 6t minus 2. Okay, so is x a function of t? Sure. What kind of function is it? Linear. Is y a function of t? And it is also linear? Okay, so we suspect then that so first of all, are ordered pairs xy a function of t? Definitely. For any t, you're only going to get one ordered pair xy. And since x is a linear function of t and y is a linear function of t, we might suspect that the parametric function, where you look at ordered pairs as a function of t, would likewise be linear, right? This would be a very reasonable hypothesis, right? So how can we verify that? Well, we can verify that by, if we took these two equations and eliminated t to get an equation of x and y, then we could see if we could write y as a function of x. Okay, and then whatever the graph of that y as a function of x would be the same as the graph of this parametric function. Does it make sense? So how can we want to eliminate t out of these two. So we could use elimination or substitution. So substitution would look like solving this for t, and we would get x plus 3 equals 8t, right? And then t equals x plus 3 over 8. And then what would y equal? If t is x plus 3 over 8, then y equals negative 6 times x plus 3 over 8 minus 2. So this is a common technique that you'll use, so when it's applicable. All right, so if we do the math here, we're going to get, what, negative 3/4 x. And then I'm going to get negative 9/4 minus 8/4. Is that minus 17/4? Check my math. So it's going to be negative 3/4 times 3, negative 9/4. Did I do it right?
Yeah.
Okay, so what did I get? So is our hypothesis correct? So y equals negative 3/4 x minus 17/4, which is a linear function, right? That's a linear function. And so what's the relationship between the given parametric function and this linear function? So the parametric function, x equals 8t minus 3, y equals negative 16 minus 2. And what we came up with here, y equals negative 3/4 x minus 17/4. What would the relationship of those two things be? Equivalent. So in what way are they equivalent? She's saying they'll show the same graph. So it'll be the same set of points. Is it the same function? Is this the same function as this? So first of all, let's see. So I'll graph the original one in blue, and then I'll do y equals negative 3/4 x minus 17/4, and I'll do that in red, and red plus blue equals purple, indigo, right? So if I turn off the red one, you see that it's right on top. So same set of points. Same function? No, it's different function, right? So parametric function, it's two different functions expressing the same points, right? It's two different functions expressing the same points. Okay, so now that I have, suppose I started with this, and I wanted to make this into a parametric function. Suppose I started with y as a function of x, and I wanted to write a parametric function. So do you see that 8t minus 3 and minus 6t minus 2 has seemingly no relationship to what we're given? You see that? So what would be a way? So all we have is that y is negative 3/4 x minus 17/4. What would be a way to express that as x is a function of t and y is a function of t? Very easily. So how could we do this very easily? Anyone have an idea? No, but so we don't know any of this, right? All this work that we did to get from here, so we're just going to start right from here, right? We're going to start right from here, and we want to write this as a parametric function. So we could just simply make x what? They need to be both functions of t, right? Functions of t, right? They need to be functions of t. How about if we made xt? Then what would y be? If x is the same as t and y equals this, then y would be negative 3/4 t minus 17/4. See what I did? So given a function y is a function of x, this is one way to parameterize it. So this is like parameterizing that function. X equals t, and y equals negative 3/4 t minus 17/4. All right, so now new question. So how do these compare? How does the original parametric function and this new parametric function that I wrote, how do those compare? So will this give the same points? All right, let's do this one too. So I'll just so t and what do we say? Negative 3/4 t. So I'm going to turn the y as a function of x off. Make this one red now. So what are we going to see when we graph? Same points or not? Is the blue one still there? Should be. Got swallowed up by the red. Yep, so they're both there. So are these two the same function? Is the original blue function the same as the red function? Maxim, you're shaking your head. No, why not? Okay, yeah, so if x is 8t minus 3 here x is just t. And y is minus 6t minus 2, and here y is this other thing. So how is it that those then are different functions? So what happens when you put in, say, t equals 1? When you put in t equals 1 into this first one, what correspondence point do you get? 5, negative 8. And we put t equals 1 into this one, you get 1, negative 5. So for the same t value, you're getting a different correspondence point. When you take all the correspondence points, the whole set matches, right? It's the same set, it's still the same line. But for values of t, you're getting a different correspondence point for each value of t in each function. So they're different functions, right? They're different functions, but the dependent set, or the set of all correspondence points, is the same. Does that make sense? That's an important point. Okay, another thing is, I want you to find dx dt and dy dt for both of these functions, right? So find dx dt for this one and dy dt, and find dx dt and dy dt for this function. Did I finish the sentence? I don't think I did. So, and then all right, so dx dt for the blue version, dx dt for the blue version of the function was 8, and for the red function is? Oh no, dx dt for the red.
Oh, 1.
Yeah, so for our blue function, dx dt was 8, and for our red version, dx dt was 1. What's going on here? Now that we know what those numbers mean, so Nick, tell me, what do those numbers 8 and 1 mean, and what do they tell us about these two functions then?
For every change in time, the corresponding change for x, the corresponding change in x is 8 times the change in t.
Okay.
And it says that the x's are changing at different rates in both those equations.
Right, so it's kind of like thinking about how points are generated, right? So when you change t a little bit, what happens, what gets generated in the blue function versus what gets generated in the red function? So when you change t a little bit, what happens with the blue function? So think about it in terms of generating points, right? So what happens with the blue function versus what happens with the red function when t changes a little bit? Josh, what were you saying? Oh, sorry. Cody.
I was explaining that because the changes in t are the same, that means the x's have to change differently.
Okay.
Because one is 8 and one is 1, so we know that if we go from 0 to 1 t,
Okay.
we know that dx is some interval with changing like respect to 8, whereas 0 to 1 is the interval 0 to 1 for the red one. It's just the x is changing with respect to about 1.
Okay. So not with respect to, but just changing 8 or changing 1. Yeah. Yeah. So that was good. That was really good. Okay. So let's see that in action here. Let's turn this one on red, right? This is red. So think about points being generated on this line, right? Points being generated on this line. For a little change in t, we get 1 times as many changes x as t, but for a little change in t, we get 8 times the change in x as the change in t. So if you think about how points are generated on this for changing t, how are points generated on the blue version versus the red version? 8 times faster, right? So the blue version of the graph, the function. Now those are x coordinates, right? So the x coordinates are being generated 8 times faster in the blue version, the original version that I gave you, versus the red version, the one we came up with over here. Okay, so like I said, 5 p.m. tonight, you'll know for sure all the homework's updated.